Hello everyone, welcome to the course on electromagnetic theory and interference. In this session, let us see various scales available in the Smith chart. So we know that the impedance of a transmission line, which is a combination of resistance and the reactance, is converted into constant resistance circles, which are the blue circles here, and the constant reactance circle, which are the red ones. The superposition of the constant resistance and constant reactance circles is a complete Smith chart, where we can see towards the center of the Smith chart is the prime center available. Then open circuit position is available to the right side of the Smith chart, and short circuit towards the left, and the above the real axis of the Smith chart, real part of the reflection coefficient, above it is positive reactance, and below the axis it is negative reactance. This is the susceptance, and here it is inductance. Now let us see, there are primarily three major scales available. One is towards the generator, okay, that will be measured in clockwise direction. Other one is wavelength towards the load, which is measured in anti-clockwise. So if we can observe, the complete Smith chart is having a distance of lambda by 2. It started 0, and here it is 0.25 lambda, and here it is 0.5 lambda. That is complete Smith chart make a distance coverage of lambda by 2. And what about the third scale? That is the angle of reflection coefficient scale, that is given in this blue color. Here you can see angle 0 here, 10, 20, like that it goes, 90 degree, 180 degree, and here 270, and again comes back to 360. So this is the angle of reflection coefficient circle, which is measured in anti-clockwise. So if you could see the Smith chart, the superposition of constant resistance and reactance circles, okay, and if you want to find out a 0.25 plus j 0.5 location, we have to see the superposition of the intersection of 0.25 R circle and 0.5 the reactance circle. Above the axis it is positive, right? So this is a location. Taking this as a point and O as a center, this point as a radius, okay, this distance is a radius, we have to draw one circle that is called constant VSWR circle, that we see in the next thing. Apart from the R circle and X circle, we need to draw the S circle, that is constant SWR circles. So these circles have the values ranging from 1 to infinity. 1 means at the origin, the VSWR value will be 1, okay, and if it extends, outermost circle is R equal to that SWR value will be infinity, okay. And the value of standing wave ratio, how we will determine, where the S circle crosses the real part of the reflection coefficient axis. Suppose here, if you could see, this is the real part of reflection coefficient axis. Right here, the VSWR circle is crossing R equal to this 5 value. So VSWR is 5 here. So both the reflection coefficient magnitude and SWR are related. So the magnitude of reflection coefficient, we know that it linearly varies from 0 to 1 as we move from the center. Center reflection coefficient is 0. As we move towards outside, it is 1. We have seen this in the last session. But the SWR value ranges from 1 to infinity based on the relation between them. So we can see the open circuit towards the right of the Smith chart, short circuit towards the left, and at the center SWR value is 1, and towards the outermost circle, here this one, before the scale starts, here it is SWR is infinity, where the resistance circle is 0 there, okay. Here the resistance circle value is 1, R equal to 1 here. And one more thing to note, if I want to locate 2 plus j, we have to see the intersection of R equal to 2 circle, okay, which is here, and j x equal to 1 circle. The intersection of these two is point P1. Similarly, 1 minus j 0.5 will be located down because it's a negative reactance. So R equal to 1, j is 0.5. So here it will be given positive values, but we have to take it as negative reactance. And the intersection of these two circles is the point P2. We have seen that short circuit position on the Smith chart occurs at R equal to 0 and X equal to 0. That is, the load impedance is 0 there. In this left hand side of the Smith chart, you can observe these. And similarly, here the open circuit position occurs when ZL is infinite. In infinite impedance, if it has, the open circuit position occurs on the right hand side of the Smith chart. And we need to know that the complete revolution in the Smith chart makes an angle of 360 degree, and if I want to represent in terms of wavelength, it is half the wavelength. Okay, it started 0, and this half coverage is 0.25 and complete coverage is 0.5 lambda. Okay, the distance of the complete rotation around the Smith chart is lambda by 2. And there are three scales that are present in the Smith chart. Okay, we need to find the input impedance of the transmission line at a certain distance from the load, right? So we need to move sometimes towards the generator, we have to find the distance, and sometimes towards the load, we need to find the distance of the transmission line. For that, we have these scales. The outermost scale, if you could see, that is the used to determine the distance on the line from the generator in terms of wavelength. From the generator, here it is 0 lambda, here it is 0.12, and here it is 0.25. Yes, and again the answer 0.5 lambda. And the next scale lying inside is wavelength towards the load. Second scale is wavelength towards the load, determines the distance from the load end. From the load end, how much distance? And if you could see, it is measured in anti-clockwise direction. So here it is 0, we have to rotate anti-clockwise. Here is same 0.25, and again ends at 0.5 lambda. And if you see the innermost scale, it is an angle of protector scale. It is angle of reflection coefficient. So it starts at 0 on the right hand side of the Smith chart, and moving anti-clockwise, we get 45 degree, 90, and 180 degree complete half the rotation. Then again the negative scales are given down. And one more thing to note, that we position of Vmax and Vmin. So voltage maximum, where it occurs, whenever the input impedance is maximum, voltage max is occurring, and it is lying on the positive axis of the reflection, real part of the reflection coefficient. Similarly, voltage minimum is occurring on the negative part of the real part of the reflection coefficient towards the left hand side. And if you could see the distance between Vmax and Vmin, it is quarter wavelength, that is 0.25 lambda. Here it is 0 and it's 0.25 lambda is covered here. And we should note that the Smith chart can be used as both impedance and admittance chart because of the reciprocal relation between them. In the admittance chart, we will represent normalized admittance as Y divided by Y naught, that is equal to conductance G plus susceptance JB. Okay, this is corresponding to the R circle and X circle that we saw in the impedance chart. So we can finally conclude that using the Smith chart, we can find reflection coefficient, both magnitude and angle, input impedance or input admittance, the location of Vmax and Vmin, provided characteristic impedance of the line, load impedance. Yes, this characteristic impedance of this line, transmission line, is that not, load impedance should be given, the length of the transmission line L should be mentioned, and the wavelength. All these parameters, if they are given, we can find these unknowns. And apart from these finding the characteristics of Smith chart, in single stub matching, Smith chart is used to find the distance of the stub from the load and also the length of the stub. This we will see in the upcoming session. So these are the summary of the Smith chart scales available here. Hope you understood the different scales. Let us start doing the problems in the next session. Happy learning. We will meet next time.